Hello. So in this video we're moving on from learning about how to find the correlation coefficient and what we can do with the regression line to look at examples of relationships like polynomial relationships, y equals ax to the n, or exponential relationships, y equals kb to the x, and using logs, the rules of logs, to turn those expressions into straight lines so that we can use the correlation coefficient and the regression line information to verify and learn about those relationships. So starting off with our polynomial relationship, y equals ax to the n. If we want to turn that into a straight line of the form y equals mx plus c, we can start by taking logs. So we have log y equals log of ax to the n. We can then use the first rule of logs that says that log a plus log b is the same as log ab to split up our log ax to the n. So that becomes log a plus log of x to the n. And then we can use the rule of logs that turns indices into coefficients. So we get log y equals log a plus n log x. And comparing that with y equals mx plus c, capital Y, y equals mx plus c is our log y variable. Similarly, our capital X variable is now log x. That leaves us with n as the gradient and log a as the y-intercept. Similarly, if we had an exponential relationship like y equals kb to the x, again we can take logs of both sides, we can split up the log kb to the x term, and we can use the rule that says the indices can become coefficients, and that leaves us with log y equals log k plus x log b. So capital Y is still the same variable, log y. Our x variable is now just x rather than log x. Our y-intercept is log k, whereas it was log a, and our gradient is now a logarithm. Our gradient is log b. So as it says, by plotting the relevant variables on the axes, we can see if the relationship is a straight line and also find the missing values. So for the polynomial, we could plot log x against log y. For the exponential, we could plot x against log y. And then that would tell us if we got a straight line or a high correlation coefficient, and that would show that the linear correlation would be appropriate, and hence the original relationship would also be appropriate. And then by finding the gradient and y-intercept, again we can do that by using our calculator to find a and b. We then can put those equal, to the gradient or to log of whatever, and work them out. So in summary, assume that we have some data points and we suspect that either y equals ax to the n or y equals kb to the x. If we plot log y against log x and we get a straight line, then that suggests that y does equal ax to the n, where log a is the y-intercept and n is the gradient. Alternatively, if we plot log y against x and get a straight line, then that suggests that y does equal kb to the x, where log k is the y-intercept and log b is the gradient. Okay, we're going to take a look at one example. It's been suggested that w and r are related by the formula r equals kb to the power w. And you can see the data on the right. We've been asked to first of all find the correlation coefficient between w and r. So on my calculator, I go for menu 6, number 2, y equals a plus bx. I type in the data as shown, and then we go for option 4, regression calc. And my calculator says the following: y equals a plus bx, a equals negative 29 point all that, b equals 4.4 and all that. I don't want either of those. A is the y-intercept, b is the gradient. The correlation coefficient is r equals 0.8346206697, so about 0.835. That is a good correlation. However, I've now been asked to find the correlation coefficient between w and log r. So the w values remain the same, but the r values, we take the log of those, and when we type those on the calculator instead of the r values we had before. And this time my calculator says this. Again, we've got a as negative 0.482-ish, b is 0.1046-ish, but r, the correlation coefficient, is 0.99955, etc. Okay, so we did get a strong correlation coefficient before, reasonably strong, 0.8-ish, but now we've got 0.99955, so that is a very almost perfect exact correlation. So given that very strong correlation coefficient, we can safely assume that r does equal kb to the w, And we can use the gradient and y-intercept information that we got to work out the values of k and b. So given that for w and log r, the y-intercept was negative 0.4823 and the gradient was 0.1046, find the values of k and b, both to 3 significant figures. So firstly, I'm just going to go back to where we came in with the exponential. We had y equals kb to the x earlier. We can convert that into r equals kb to the w just by changing the letters. And as we go through the process of turning that formula into a straight line, we see that we get log r, we get w, but we get a y-intercept of log k and a gradient of log b. So if the y-intercept is log k, and we also have a value of negative 0.4823, then we can solve the equation log k equals negative 0.4823. We can raise both sides to the power of 10, so k equals 10 to the power of negative 0.4823, which is 0.329 to 3 significant figures. Similarly, if the gradient is log b, then that means that log b equals 0.1046. Again, raising both sides, power of 10, b equals 10 to the 0.1046, so b equals 1.27 to 3 significant figures.